Buon pomeriggio, io sono Maria Elena e faccio parte del gruppo Giovani di Bergamo Scienza. Prima di iniziare vi chiediamo un momento di attenzione e vi ricordiamo che per la traduzione simultanea è sufficiente scannerizzare il QR code che trovate indicato sulle porte della sala o proiettato alle mie spalle. Il QR code vi indirizzerà direttamente a Converso Web App, dove potrete selezionare la lingua di interpretariato dal menu a tendina. Per l'ascolto della traduzione è necessaria una coppia di auricolari. Vi chiediamo la cortesia di utilizzare le vostre, ma chi ne fosse sprovvisto può chiedere ai volontari in sala. Vi invitiamo a seguirci sul nostro profilo Instagram, dove quotidianamente vi raccontiamo il festival, e ad interagire con noi taggandoci nelle vostre stories. Vi preghiamo di silenziare i vostri apparecchi elettronici e di partecipare numerosi alle iniziative di Bergamo Scienza. Grazie per l'attenzione e buon ascolto.
Buon pomeriggio, ben ritrovati per un altro evento a Bergamo Scienza con l'Agenzia Spaziale Europea. Io come sempre desidero ringraziare gli organizzatori del festival e tutti i volontari che ogni anno rendono questo evento possibile. Sono molto felice di vedere che oggi la sala è piena e quindi che questo tema affascina e interessa tutti. E soprattutto che ci sono molti giovani in sala, questa è una bellissima cosa. E tra l'altro volevo solo fare una piccola digressione spaziale, vi chiederei di farlo con un applauso perché oggi stanotte è rientrata dallo spazio la nostra astronauta Samantha Cristoforetti. Dopo ben 6 mesi nello spazio, una grandissima avventura, una grande donna che io sono onorata di avere come collega. Ma oggi abbiamo un'altra grande relatrice che sono molto contenta abbia accettato il nostro invito di venire a Bergamo Scienza, anche se purtroppo non è qui fisicamente con noi perché ha avuto dei problemi di salute, ma è collegata da Monaco. Ve la presento subito brevemente. Si tratta di Linda Tacconi, che è Senior Scientist presso il Max Planck Institute for Extraterrestrial Physics. Lavora dunque vicino a Monaco di Baviera, ma in verità è americana. Ha studiato e ottenuto un PhD all'Università del Massachusetts e ha lavorato per alcuni anni prima di arrivare al Max Planck Institute presso la fondazione olandese per la ricerca in astronomia, quindi è in Europa da molti anni. E la dottoressa Linda Tacconi ha ricevuto numerosi premi, fra i quali il Lancelot Berkeley Prize, in riconoscimento per i suoi studi nella formazione delle galassie, di cui appunto ci parlerà oggi. Inoltre è entrata a far parte della Royal Swedish Academy of Sciences per il suo straordinario contributo alla ricerca nel campo dell'astronomia millimetrica, che ci spiegherà anche di cosa si tratta. Presiede inoltre il consiglio dello European Southern Observatory, che si trova in Cile, che forse è l'osservatorio astronomico più importante che abbiamo sulla Terra, o uno dei più importanti sicuramente, e ultimo ma non da ultimo ha presieduto il Senior Committee dell'Agenzia Spaziale Europea per definire i futuri programmi, le future missioni dal 2035 al 2050. Ed è proprio in questo contesto che ho avuto l'onore e il piacere di sentire una sua presentazione fatta appunto al comitato scientifico dell'ESA ed è stato in seguito a questo evento che mi sono detta che sarebbe stato bello condividere anche con voi l'emozione che ho provato ascoltandola. E quindi sono molto contenta che Linda abbia accettato il nostro invito e che sia qui oggi con noi per svelarci i misteri dell'universo primordiale e le origini delle galassie. Vedo che siete numerosi, infatti chi di noi, alzando gli occhi al cielo, non si è mai posto, no? Le domande in una notte di stelle, le domande legate all'universo, alle sue origini. Non so se ieri sera avete seguito anche voi la conferenza con il premio Nobel per la medicina Craig Cameron Mello. Anche lui ieri ha fatto una breve digressione parlando del Big Bang e delle origini dell'universo. È dunque un tema che affascina l'uomo fin dalla nascita, insomma, dell'uomo. E oggi è grazie anche alle missioni spaziali dell'ESA che abbiamo una visione dell'universo straordinaria come non l'abbiamo mai avuta nel passato, e questo grazie a strumenti come l'Hubble Space Telescope, il James Webb Space Telescope o la missione Gaia. Quindi possiamo vedere delle immagini delle nostre galassie, la dottoressa Tacconi ce le mostrerà più in dettaglio, immagini che i nostri antenati non hanno mai potuto vedere. E quindi l'ESA, il cui mandato è fare ricerca scientifica per scopi esclusivamente pacifici, ha infatti tra i suoi programmi quello della scienza e mette a disposizione della comunità scientifica dati straordinari che permettono agli scienziati di tutto il mondo di comprendere meglio il nostro universo. E fra questi scienziati, quindi come vi dicevo, c'è la dottoressa Linda Tacconi, alla quale cedo subito la parola. Linda, grazie. The floor is yours.
Thank you so much, Ilaria, for that wonderful introduction. And thank you also very, very much for inviting me today. And I'm very, very sorry to miss being there in person. That's just the way things are these days. I especially wanted to come in person because my grandparents, my mother's parents, in fact, are grew up very close to Bergamo, in fact, north of Bergamo. And so I wanted to come back and see where they, what they left behind when they moved to the US about almost 100 years ago. So what I want to tell you, in fact, is when they were doing that, moving 100 years ago, we almost didn't even know that there were galaxies outside of our own. And so what I want to tell you today is what we know about our own galaxy and how we use that to also look back in time to understand how galaxies grew to become things like the Milky Way, or even more massive galaxies, or also less massive galaxies. So the next 40 minutes or so, I'd like to talk with you and with Ilaria, our hostess, and try to explain a little bit more about what we know. So let me start by just going, for some reason I don't know why it's not advancing. There. So a quick timeline of the universe. Basically, we know that there was a Big Bang, or we propose there's a Big Bang, more than 13.5 billion years ago. And at the time, right after this explosion, there was such an amazing amount of energy, but there were already a few fluctuations that we could see, that were there, that were the seeds of everything else that we see today. So a few 100,000 years after the Big Bang, things started cooling down, and they cooled and cooled and cooled, and the first structures started to form. The first stars, the first galaxies, that's what we know. It's very hard to see those at this point. Then over the course of the next billion years or so, we have a picture where the structures were forming, growing ever bigger, merging in a way, and then those first stars, those first galaxies acted to reheat the universe and caused what we call the epoch of reionization. The galaxies at that point were quite young. There were also seeds that had not yet formed. And in the next billion years, and right here at about 4 billion years ago, this is where I'm going to spend most of the presentation today, at a time that we call cosmic noon, but what I like to think of as the teenage years of galaxy formation. And then ultimately, we move closer to our own time in the universe, where we see many, many galaxies, beautiful galaxies, spirals, elliptical-like galaxies. And I want to tell you a little bit about, that's where I'd like to start, and from the present day and work a little bit back in time. So let's start by looking at a movie that was created by Professor Tully at the University of Hawaii, where we start in our own neighborhood and we're moving very fast to look now through the galaxy. We're seeing 150 light years away, some of these beautiful star-forming regions, the Orion Nebula, the Horsehead Nebula, where massive stars are formed. Here comes another one. This is called the Rosette Nebula. We're now going towards the center of the galaxy. We see a supernova, an explosion of a massive star. And as we leave the galaxy, we can see that the galaxy is made up of, in the center, very, very bright, dense amount of stars, and then gas. And then we're now leaving the galaxy behind. We're going to our nearest neighbor, the Andromeda galaxy. We're flying through another neighbor, the Messier M30, it's called M33. Then we leave our immediate neighborhood, see some other very beautiful galaxies. We're headed towards the center of the Virgo cluster, which is 50 million light years away from our own galaxy, but that's still considered our local neighborhood. And you see the various shapes of galaxies, some spirals, some ellipticals. The most massive galaxies, like the one at the center of Virgo, the famous M87, where we imaged the black hole with the Event Horizon telescope, is some of the most massive galaxies we know. So then we end the movie with a picture of what the Milky Way probably looks like. It's hard to see it because we're in the middle of the Milky Way, so it's very hard to see the exact structure of the Milky Way, but we know that we have spiral arms and the center, and there's this dark material, which is the interstellar medium, and that's where future stars can form. So a schematic of our own galaxy. Let's look on the left here. This is looking at it from the top. If we could look down somehow at our galaxy, we see the central regions. It's called the central bulge. We're located, that is also where the supermassive black hole, Sagittarius A star, is located in our galaxy at the very center. Then we see where we are located here, our solar system. We're about 27,000 light years away from the center of the galaxy, out in the disk. We see the beautiful spiral arms where bright new stars are forming, as you saw in the movie. We saw a couple of those. And then and further out, the light starts getting fainter as the fewer and fewer stars. The whole galaxy is about 100,000 light years across and contains about 100 billion stars. Sounds pretty amazing, but it's actually a very typical galaxy. It's not, it's rather massive as we know, but it's not the most massive objects that we know of. If you look to the side here, you get a side view. You can see not just the disk here and the central bulge, but you also see that we're surrounded by a halo of some of the oldest stars that we know. And this is where some of the ESA satellites, especially Gaia, are providing some new insights about those stars. Now let me continue with the local universe by just showing you some of these beautiful galaxies in a little more detail. And I'll try to comment a little bit on each one. This is our nearest neighbor, the Andromeda galaxy. It's a little bit more massive than the Milky Way. You can also see it has some smaller satellite galaxies around it. I mean, other galaxies, so you can see this dark material, as I pointed out. is the future sites of star formation. You can see these galaxies, these spiral galaxies that show two very prominent arms, bright center, and it almost looks like material is flowing in. This is an image that was just provided by the James Webb Telescope, which provides a whole new view of a nearby galaxy at scales that we could only dream of a few years ago. M51, the famous whirlpool galaxy, whose bright spiral arms are probably driven by this interaction with its smaller neighbor. Galaxy mergers, not so common, but we do see them. This is where stars form at very high rates in the local universe. And you can see a few examples of these galaxies that are smashing into each other or interacting with its neighbors. We also see more elliptical-like galaxies, which have undergone also a merger and are injecting material from their supermassive black holes back out into space. And here's another example of one of the most massive cases of that, where these bright plumes of actually radio emission are heating up the region around the galaxy. And then this, the famous sombrero, is more like the kind of thing that we think much of what we study at the early universe evolves. Much of what we can now study at the early universe becomes something more like this. And so keep this in mind. This looks a little bit different from our Milky Way or Andromeda or M51. And then in the center here, I just wanted to show you one example of not all galaxies look so ordered. The ones that we see in the local universe that are of lower mass. So these galaxies are all typically of 100 billion times the mass of the sun, these kinds of things. This one maybe is even even 10 times more massive than that. But this galaxy, the Large Magellanic Cloud, which is in the southern hemisphere, is only about a tenth the mass of the Milky Way. And it doesn't have the gravity to be able to form a very coherent disk or spiral arm. Well, so this is what we can see. This is all considered within the nearest 100 million light years or so from us, and we can study these galaxies with a precision of a few tens of light years by now with a modern instrumentation.
Questo è veramente affascinante. La dottoressa Linda Tacconi ci sta portando in un viaggio interstellare veramente meraviglioso con queste immagini straordinarie. Però ecco, volevo chiederti, Linda, ma come fate voi scienziati, che abbiamo parlato ovviamente dei telescopi da terra, delle sonde dell'ESA, però come fate voi scienziati per studiare le galassie, in particolar modo l'universo primordiale, e soprattutto che cos'è la interferometria millimetrica?
Okay, so let me address the second part first. So we use the electromagnetic spectrum, which is just light, to study the different properties of galaxies. So here at about 380 nanometers to 700 or so nanometers is what we call visible light. This is what we see with our eyes. But astronomers use the full spectrum from the most energetic light with the shortest wavelengths, gamma rays, X-rays, to study things like black holes and neutron stars and the most explosive events in the universe. We also used ultraviolet light in satellites, from satellites that can show us information about the youngest stars or supernova remnants, for example. But where most of the research that, in fact, I have been working on is at the longer wavelengths. It's at the infrared, the thermal, the heat, what we sometimes call heat radiation. This is longer wavelength, more like a micrometer or to 3 micrometers, or even further. It's called the near infrared to mid infrared. This is where we study cooler stars, warm gas, molecules. The millimeter wave range, which you asked about, is sometimes also called the microwave range, and there's where we're studying these very cool clouds of gas around newly formed stars, or gas that's not yet formed stars. It's the food that galaxies eat to form new stars. So if you think of it as it's the food for star formation, and that's mostly makes itself known through infrared and millimeter or microwave emission. And then even longer, the radio waves that can go all the way up into meter wavelengths. We can see also other tracers of the neutral gas, the atomic hydrogen, and also what's called non-thermal emission of very energetic electrons moving in magnetic fields. So that's our sort of, that's what we have at our disposal to understand different processes for how a galaxy forms. But in Europe, we are so fortunate right now to have, both on the ground and in space, a huge number of some of the best facilities in the world. I actually have to say, this is something that we really in Europe should be very proud of. We have in the optical near infrared regime, the ESO, the European Southern Observatory, a very large telescope. The headquarters of ESO are located here in Garching. The telescopes, of course, are given the skies in Germany. We don't want to have telescopes here so much. So the largest telescopes are located in Chile, in the Atacama Desert. And the ESO very large telescope is located on Cerro Paranal, north, about 2.5 hour flight north of Santiago de Chile. But we also then have access, ESO is also part of the ALMA array, which is the largest array of millimeter telescopes at a 5,000 meter plateau in very north of Chile. But in the Northern Hemisphere, we also have access. 3 countries, Germany, France, and Spain, have built the NOEMA array, which is located not too far from you on the other side of the Alps in southeastern France. In space, then upcoming, by the end of the decade, Europe will have the largest, the most powerful telescope ever built on the ground, the 39 meter European Large Telescope, or the ELT. That's currently in construction. You can go to the ESO web pages and see a webcam and see it, the construction progress. And we will be in Europe will be the first to have such a facility, and it's extremely will be extremely exciting to see what it provides. I'll come back to that a little bit at the end. In space, the European Space Agency has led some very important missions. For example, the Gaia mission, which I'll show you a few slides about, which shows the positions and motions of over 1 billion stars in our own galaxy. In the X-rays, we've had XMM Newton, which tell us something about black holes. ESA also led the amazingly successful Herschel mission, which was launched in 2009 and provided a new insight into the dust and gas in galaxies. And then, of course, ESA is also participating in Europe. We are participating in the Hubble Space Telescope and now with the James Webb Space Telescope. So we really have an amazing toolbox to study all the physical phenomena and how a galaxy might form.
Yeah, you mentioned the Gaia mission of the European Space Agency. Oh, scusate. Scusate, devo parlare in italiano. Dicevo, Linda, hai nominato la missione Gaia dell'Agenzia Spaziale Europea, che ha dato un contributo veramente fondamentale a voi scienziati e alla comunità dei ricercatori in Europa per conoscere meglio la Via Lattea. Ce ne puoi parlare un pochettino più in dettaglio?
Yeah, I wanted to, in fact, highlight a little bit about the guy. Sorry, let me skip this. This was just a picture that shows how the different wavelengths of light give you different information in one particular galaxy. So from the radio, the millimeter, the optical, you can see that if you piece all of this together, you get a much better idea of how what's really driving the physics in a galaxy. But let me move on to Gaia. So the Gaia mission, which was launched in 2013, as Dr. Zivioli has said, is really a source of pride for Europe. It's a mission that has world impact. Thousands of people are using the information from Gaia to understand how the Milky Way formed in a subject called galactic archaeology. So what you do in galactic archaeology is you look in your own local universe in detail at the individual objects and try to piece together how it all got that way. So Gaia has been able to provide for astronomers almost 2 billion positions for stars, and looked at in various colors of light, blue, white, red, up to almost 2 billion stars. It's also been able to track the motions of these stars, which is something that has never been done to this precision before. So let me give you, and as I said, it's amazing how many scientists, how many papers, if you look in the astronomical literature, every week there's tens and tens of papers, all coming from Gaia. And this is something that ESA Europe did on its own, and it's really transforming what we know about our own Milky Way. Let me give you an example. This is from a beautiful work from led by a professor in the Netherlands, Mina Helmi, where she showed, based on Gaia, and this is a simulation now, that about 30 million stars that are shown here in red crashed in, it's a small galaxy, crashed into the Milky Way. Now these stars were identified by Gaia as having different motions, different sense of motion. And what we think has happened is that this event, which happened about 10 billion years ago, which is the timeline that I'm going to be talking about for the rest of this presentation. This was, although it was only 30 million out of the 7 million stars that we so far have these accurate velocities, this shows that this kind of a minor event could likely have driven very important structural differences in our galaxy, such as it created what's called a thicker disk, so the disk above and below where we're living. It might have even driven the formation of the central bulbous material. It would cause some material to fall into the center. It may have even helped to feed our galactic center black hole. So Gaia has provided a picture of events of the Milky Way's history through this study of galactic archaeology that we didn't know before the mission. And it's just every week, as I said, every week, every month, there are more papers coming out where researchers all over the world are using the this immense database that Gaia has provided to learn more about our Milky Way galaxy.
Grazie, veramente è affascinante, non so voi, ma io rimango sempre senza parole di fronte a queste immagini straordinarie e a quello che gli scienziati riescono a farci capire, quello che riescono a studiare andando indietro nel tempo. Ma giustamente, Linda, andando indietro nel tempo e uscendo dalla nostra Via Lattea, dalla nostra galassia, com'erano, visto che il centro del tuo studio, il cuore del tuo studio è proprio quello dell'universo primordiale, com'erano le galassie primordiali, quelle ancora più antiche rispetto alla nostra galassia, o comunque com'erano al loro inizio?
Okay, so most of what our team does is look at galaxies as they were. We don't look at the Milky Way so much, we look back in time. And because light takes a finite time to get here, what we're able to do now with the powerful telescopes like the HST and now with James Webb Space Telescope, but also the ESA Very Large Telescope, is to look at galaxies because as the universe expands, we know that through the Doppler effect, we can take wavelengths of light or emission lines, and they're redshifted into a different part of the spectrum. And based on that information, we can tell how long the light took to get to us. And so we know that these young galaxies are galaxies as they were 10 billion years ago. So 3 billion years after the Big Bang. So this is what I would call the teenage years. Galaxies at that point look very chaotic. As you can see here, they look much more like the kind of merging systems that I showed you earlier in the talk. They're bright, they have clumpy, bright structures, but there's not so much detail. Now, part of the reason that there's not so much detail is, of course, they're so far away, and our telescopes, as powerful as they are not able to provide the really sharp images like we have in our own beautiful surroundings out to, say, the Virgo clusters, which is what I showed you at the beginning. But, we still are able to get quite a bit of information from these galaxies.
Ma aiutaci magari a capire la differenza tra le galassie primordiali e le galassie più recenti. Qual è la differenza? Ci sono dei parametri anche fisici o dei processi fisici che le caratterizzano?
Yes and no. So when we look at them, as I said, they're all clumpy. And what we also then have tried to do, we have information by now on the structures of these young galaxies for thousands and thousands and thousands of galaxies out in this young universe, in this what we in astronomy sometimes call cosmic noon, or as I like to call it, when galaxies were more like teenagers. And we tried to make some order out of this. And so in this diagram, we've just taken a few hundred of them just to show you that this clumpy, irregular structure is not just for a few galaxies, but that we really, it's most of the galaxies that we see. So if you put them in a diagram where you look at how fast they're forming stars versus how massive they are, you try to see, do they get more chaotic, less chaotic as they form more stars or less stars? And what you can see is that maybe a little bit over here where they're not forming so many stars, they already look more like these elliptical M87 or sombrero-like things. But, and these are already very massive, even 10 billion years ago. So these galaxies grew very, very, very fast. Because this over here, these galaxies here are already having the mass of our own Milky Way. But this was already 10 billion years ago. So when we study galaxies that 10 billion years ago, which is often what we're doing, were already the mass of the Milky Way. Those things become more like these very, very massive structures, as galaxies in our local universe. Down here, which is where we form, where these things will probably become more like the Milky Way. But as you see, this clumpy, chaotic structure looks the same throughout this diagram. So the question is, well, what is making this chaotic structure? And what do we know about these chaotic galaxies? So they look, the other thing we know about galaxies in the early universe, so 10 billion years ago, is that they formed stars much, much faster, 20 times faster in a typical galaxy than what you see in our Milky Way. So a galaxy like the Milky Way is formed, or the other spiral galaxies are forming stars at a rate of about 2, 3, 4 masses of the sun per year. In the early universe, we are seeing things that are over 100 solar masses per year, or even more. In our local universe, there's only one thing that drives that, and that is galaxy merging. When you take two galaxies, you smash them into each other, you cause an increase in star formation, rapid increase in star formation. And that was something that 15 years ago, the astronomers thought, oh, that must be what's happening, because we know that structures are coagulating in the early universe. So it must be that galaxies are merging, and that's how all galaxies are forming. But actually, since then, we think that it's a more slow process, a more not quite so violent process, where we see material flowing, where we think material from the immediate halo of the galaxy is falling onto the young galaxies, and that is what's fueling this star formation, this increase in star formation. This result is a very famous result from the Hubble Space Telescope about 10 years ago, and people have been trying to address this issue since then. So we know that, yes, these galaxies are different because they form many, many more stars. And in fact, in that time frame, and this was the time frame when the Milky Way probably had its merger, did have its what's called the minor merger. A galaxy like the Milky Way assembled 70% of its stars in this time period, 5 to 10 or 8 to 10 billion years ago, including probably our sun. Now, another thing we know, we've been able to study with the millimeter interferometers, and this is work that I have been focusing on a lot in the last decade, is how much fuel for star formation is in these early galaxies. And what is plotted here is as a function of look-back time. This is where here is the time of where we are currently, our present time in the universe. If you study the amount of cold molecular gas, or the food for star formation, as you go back in time, you see that it is increasing by a huge amount, almost the same as what we see in the star formation rate, which is one piece of evidence where we think that it's just that because the universe was smaller, the accretion onto these galaxies was much, much faster in the past. And it hit a peak exactly about 10 billion years ago before it started running out of steam. And then you see this fall off. It's just because the amount of fuel that's available, there's not as much coming into the galaxy. So once you use it up, you will start to use up most of your fuel, and then you get to where we are in the current universe, where you are forming, as I said, 2 or 3 times the mass of the sun in new stars per year. So this was also a fairly important piece of evidence that said, well, maybe it's not that it's mergers, it's more of a more peaceful process of just material coming in, lots of food available, and these galaxies are growing like crazy at this point. producing lots of stars and using up this fuel. But so does that mean that they're different from our galaxies? Well, the real answer came when we could also study the motions of the individual regions in the galaxy. So on the left here, I'm showing you a spiral galaxy, a local spiral galaxy, just as an illustration, which you can download from the web, where if you look at the motion, if you look at an emission line, a spectral line in the center, you'll see it at sort of this frequency. Now, the motion of the galaxy, we know that local galaxies are rotating. As you look on this side, which is the side that's moving away from us, you'll see the line shifted over to the red a little bit in the Doppler motion. Whereas on the other side, you see it coming towards you. So if you make a simple model of what this looks like, just a very stupid, simple galaxy model, and you can do this on any computer, where you just take a distribution of light in a galaxy, and then you give it a velocity field. If it's a rotating disk like our Milky Way or like any of our spiral galaxies nearby, what you see is when you plot then the motions across the galaxy, you see this diagram, which is sometimes called a spider diagram, where here you see the gas moving away from you, and here you see the gas moving towards you along some axis like this, and it's a very ordered motion, and that's what we know about the rotation of our galaxy or of other galaxies. Now, if a galaxy is merging, you don't expect to see this. If you see this, and you will see chaotic motions from the individual galaxies, plus when they smash together, this ordered rotation will be disrupted. But when we're able with these powerful telescopes now to look at this, for example, this galaxy, which is a galaxy that we're seeing as it was 10.5 billion years ago, what we see is exactly the same thing. We see this ordered motion, moving away, coming towards us. So, and we've been able now to do this for, again, 1,000 galaxies, and more or less in 70% of the cases, not all the cases, but in most of the cases, we see this kind of, when we make these velocity plots, we see this red going away, blue coming towards us, indication of ordered rotational motion. So that tells us that these galaxies are not, having a violent, mostly having violent events happening within them. They might be having smaller mergers with some of their very low mass neighbors, but what we think now is that this more view of an evolution where material streams onto galaxies, they grow, they transform themselves into galaxies as they would look now. And so what we're seeing then in those clumpy, in these more irregular structures, is that we're only looking at them at a few different wavelengths. We don't have the full picture the way we do in our local universe. And also we're looking at material that is at shorter wavelengths than we are in the local universe. And so much of it is obscured by this interstellar dust. And so that's what gives it its chaotic image. So in this case, a picture is not worth 1,000 words. You really need that third piece of information of the motions. And that's what has led to our belief. So I would like to then show you then a typical, what a typical, like I showed you before, if you look at galaxies in different wavelengths, you also get information. So here in this galaxy I just showed you, if you look the molecular gas, we don't see the beautiful detail, okay? That's missing because these galaxies are so far away. So you really have to have some amount of fantasy to try to disentangle what's going on. But you look at this is tracing the sites of the star formation. which because it's more gas, although this is blurred, but these sites of star formation are likely much, much bigger than they are in the local universe. And this is what the stellar light looks like. Another feature that we see a lot not just in the local universe, but it's much more common in the early universe, is that we see a lot of gas flowing out of galaxies. And that's because lots of young stars produce, when they explode, they produce these outflows of material that can actually leave the galaxy. And also the supermassive, the growing black holes in the center are also can spew out large amounts of the fuel that has rained in. So we're seeing that phenomenon, which is a stronger effect 10 billion years ago than it seems to be in our local universe.
Allora, io devo dire che volevo ringraziare Linda per riuscire a spiegare queste cose complicatissime in modo che siano comprensibili anche per uno space lawyer, un avvocato dello spazio come me, che fa un po' fatica. Ma magari una domanda un po' così semplice, Linda, per te. Pensate voi scienziati di aver quindi capito i segreti dell'evoluzione delle galassie dalle loro origini fino ad oggi e aver carpito quindi i segreti dell'universo, oppure c'è ancora molto studio da fare in questo settore e c'è ancora da esplorare e da conoscere?
So, yeah, I think yes and no. Of course, there's always more. That's what research makes research so much fun, is the more you look into a question, the more questions you have. And that's what is so fascinating about science. It's so much fun to do this. But yes, so here's another example of a clumpy early galaxy. We think we understand it at the very basic level, that galaxies grow and evolve mostly in what we call equilibrium. And so what I mean by that is that we know that galaxies are material rains in, stars form in these very gas-rich environments, and then the outflows from the dying stars and supermassive black holes, which has now been enriched with heavier elements, goes back out of the galaxy, rains back in, and so you have a cycle, which we call sometimes the baryonic cycle. At that level, I think we do understand. But let me then end this part of the talk on another way that you can understand how a galaxy forms. And here's where people who the theorists in astronomy are the people who build these massive simulations of the universe and of galaxies forming, have a big advantage, although they work with us. But I want to show you now a movie from one of these simulations, which basically is, this is from the illustrious TNG team. It is showing a galaxy, which is, the simulation will start a few 100 million years after the Big Bang and will take us all the way to the present time. And I'll try to explain, it goes rather fast, I'll try to explain what's happening. But the bottom line is the galaxy at the end becomes something that's very similar to our Andromeda galaxy. So here you see this clouds of material falling onto this young galaxy a few 100 million years after the Big Bang. In the lower left, you see a larger picture of several hundreds of millions of light years. So many galaxies forming within this region, but we focus on the central one here. In the bottom right, what the simulators can do that we can't do in observing directly is you can separate this is what the stars are doing, this is what the gas is doing. So you can see that there's a lot of material coming onto this galaxy. And you can see that it's starting already, here's 10 billion years ago now, to look a little bit more ordered. This is probably the peak of where things are falling onto the galaxy, so the simulation takes you to give you a different view. This is also showing you the gas that has now evolved to have larger amounts of heavy elements. And then we continue. So down to the current. So here, this counter here is redshift. Unfortunately, it's not look back time. I'm trying to tell you in my head how far back we're now looking. We're now looking probably around 7 or 8 billion years ago. It's really starting to look much more ordered. You can see also that it's developing some smaller satellite galaxies, like we know has the Andromeda galaxies has. You see the central bulge of stars. You see the gas having spiral arms, but you see that there's less stuff coming on. And then in this particular simulation, at the very end, you see a small merger, which then ultimately, as I said, should end up something looking like the Andromeda galaxy. So what the simulators do is take physics that we know from the observations or from physical theory and put it into a supercomputer and create things that look like this. And so we work together, the observers like me, with the simulators to do counter checks on each other, to try to understand a little bit more about how galaxies might form and evolve from the early universe to our current day.
Allora, siccome ci avviamo verso la conclusione di questa meravigliosa conferenza della dottoressa Tacconi, volevo un attimo rivolgere uno sguardo verso il futuro. Abbiamo capito dalla relazione di oggi l'importanza dello studio dell'universo, l'importanza degli osservatori a terra, ma anche delle missioni spaziali che ci aiutano quindi ad avere delle definizioni magari diverse o più alte a seconda degli strumenti a bordo delle sonde, e soprattutto ci permettono un'osservazione dello spazio da un'altra prospettiva che non è quella terrestre, senza le interferenze magari luminose o di altro tipo. Quindi abbiamo fatto e stiamo facendo molti passi in avanti, abbiamo capito l'importanza della missione Gaia, tant'è che io in questi giorni sto rinnovando gli accordi multilaterali tra gli stati dell'ESA che hanno fornito gli strumenti a questa missione, perché è importante continuare a fornire dati alla comunità scientifica, che è in fondo il nostro mandato. Ma come vi dicevo all'inizio, la dottoressa Tacconi ha anche partecipato alle future missioni dell'ESA, quindi l'ESA sta lavorando, sta pensando, sta studiando le future missioni, quelle che si chiamano appunto Viaggio 2050. E fra queste ci sarà molto probabilmente, anzi quasi sicuramente, lo studio dell'universo primordiale. Allora volevo chiedere in conclusione a Linda Tacconi cosa ci aspetta in futuro e soprattutto quali sono le aspettative della comunità scientifica a tal proposito.
Okay, so let me just give 2 examples. So let me show you, probably you've all downloaded this picture, one of the first pictures from the James Webb Space Telescope, which was launched at the end of last year. This gives us the deepest picture yet of a snapshot of the universe, where we see all of the beautiful galaxies. This is now through the gravitational lens of a cluster there, where you see some of the most distant galaxies actually are stretched from the massive cluster that's before it. But James Webb so one example is James Webb Space Telescope is going to provide us, for those of us who are studying how galaxies are forming, with pictures of galaxies as they were at the various earliest stages. And so the initial images here, 11 billion years ago, 12.5 billion years ago, 13 billion years ago. This is, the earliest galaxies that we will then follow up. Once Webb shows us where they are, we'll follow them up on the ground with our, in the future, extremely large telescope, and also with the continually upgrading millimeter interferometers to look at the gas component as well. You mentioned the early universe. the very earliest phases, a few 100 million years, are still very unknown. We don't know much about that at all. And so that was one of the, the ESA, it's hoped that ESA in the future will be able to have a special mission to study the very earliest phases of the universe. Then finally, I just want to leave you with one little very rudimentary simulation. So if you take one of our beautiful 39 meter ELT will be able to do just a few years from now, before the end of the decade. So all of the young ones in the audience, I will be, retiring at that point, but you will have the opportunity to use this amazing facility. So here we take a galaxy, one of our nearby galaxies, where with our typical smallish telescopes even, we're getting to 115 light year resolution. And you've seen many pictures over the course of this talk like that. Now, if you take this galaxy and don't do anything else to it, don't make it an early galaxy, but keep it the way it is, move it out to 10 billion years ago. This is what the Hubble Space Telescope, what it would look like with the Hubble Space Telescope, or with the current ESO Very Large Telescope with atmospheric correction through adaptive optics. Now, with James Webb, the same thing would look like that. You can see already the spiral arms, the bright center, but now with the ELT, which is 39.5 meters, so 6 times bigger than James Webb. Now it's based on the ground, so we have to look through our atmosphere. But because we'll have the highest technology corrections to correct for the aberrations of the Earth's atmosphere, we will see this galaxy out at 10 billion, a look back time of 10 billion years ago, almost as clear as we see it currently today in our local universe. So it's going to be fascinating. So we will learn with James Webb about the earliest galaxies, and with the follow-up from the European ELT, we'll learn about the scales on a few hundred light year resolution that we can only dream about right now. So it's going to be extremely exciting. So with that, I would just like to say thank you, grazie, and again, I'm very sorry that I could not be there in person.
Grazie mille, Linda Taccone. Grazie infinite per questa presentazione straordinaria. Abbiamo veramente fatto un viaggio nell'universo, un viaggio affascinante, e sono sicura che ci saranno domande dai tanti ospiti presenti qui in sala, quindi direi che cedo volentieri la parola.
Grazie per questa bellissima presentazione. Voglio fare una domanda molto semplice. Vedo dai vostri filmati che praticamente i movimenti nelle galassie viaggiano spesso o quasi sempre a spirale. Quali sono le forze in campo che determinano questi movimenti? Grazie.
It's just simply gravity, and it has to do a lot with the way that the material comes in. So the angular momentum of the material that comes in on the galaxy. What I didn't show you much of were elliptical galaxies, which are also rotating, but they're spherical, big. They look almost like big balls. And those rotate much, much more slowly because they had a very different, probably a very different formation path than, say, our spiral galaxies, where most of the spirals probably, it's just like at a carnival ride where the centripetal motion as a thing is moving around, and this is all just because of the angular momentum of the material and the gravity of the disk. And so it just, as you saw in the simulation, it just all starts to spin up and to just to do this much more ordered rotation.
Grazie. Prossima domanda. Oh, che bello, un giovane.
La mia era una domanda sullo scontro fra le diverse galassie. Per esempio, se uno scontro fra due galassie, facciamo conto, la Via Lattea e la galassia di Andromeda, succedesse adesso, ci sarebbero dei riscontri per la Terra?
Probably not, because the distance, although it looks like everything is very tightly packed, actually the distance between stars is so large. I mean, our nearest star is a few light years away from us. So you probably don't even notice it. You probably would not even notice it in the solar system. Plus that process takes typically a few 100 million years. So in a lifetime of a person, you would not even notice that something was happening. You need to live for 500 or 600 million years, and I don't think we're going to get that.
Sì, decisamente parliamo su delle scale di grandezza che sono diverse rispetto a quelle a cui siamo abituati e rispetto alla lunghezza della nostra vita, soprattutto se comparata alla vita nell'universo e dell'universo. Altre domande? Là in fondo ce n'è una. Arriva il microfono, un attimino di pazienza.
Di chi è? Buon pomeriggio. Vorrei sapere se le informazioni che abbiamo acquisito sulle galassie ci possono dire qualcosa sul destino dell'universo e se le teorie propenderanno per una continua espansione o per una implosione. Grazie.
As far as we know, based on everything that we have learned, not so much about the individual galaxies, but the cosmologists who have studied the universe as a whole, the universe should continue to expand and not go back to an implosion.
Grazie Linda. Ancora qualche domanda? Questo è un argomento che suscita a volte anche domande che magari non osiamo fare. Ecco, lì in fondo ci sono delle mani alzate.
Volevo fare una domanda. Se è possibile spiegare in maniera anche abbastanza semplice quali sono i metodi con cui studiate i fenomeni indietro nel tempo. Come fate a studiare un fenomeno che è accaduto moltissimo tempo fa? Quali sono i metodi che utilizzate?
So so the methods, so if you, for example, if you look at just the light of the optical light of a local galaxy. Now, because of the expansion of the universe, that same information is then shifted into the infrared or even the far infrared or millimeter. So depending on how far away it is, you have to then, you have to look with different kinds of telescopes at the early galaxies to get the same information that you would get from an optical telescope, say, in our local universe. I don't know if that answers your question. So this is why things like the James Webb Space Telescope, which is mostly an infrared telescope. So instead of studying wavelengths of 800 nanometers or 700 nanometers, it's studying things that are 7 to 10 micrometers. So this is looking back in the universe to see the same features. So in a way, the entire optical light is shifted into that band. So without a telescope like James Webb, we wouldn't be able to see it at all. I don't know if that helps.
In questo lasciatemi dire che per fortuna abbiamo l'Agenzia Spaziale Europea che contribuisce con questi strumenti nello spazio, perché James Webb Space Telescope, che si attribuisce quasi sempre alla NASA, in realtà è frutto di una collaborazione anche con l'Agenzia Spaziale Europea. Quindi insomma anche noi europei abbiamo qualche merito in questo senso. Altre domande in sala? Ecco due mani alzate.
In fact, if I could just comment on that, two of the most important instruments, the two spectrometers, which tell us about the physics of the galaxies, were built in Europe. So and Europe, of course, launched the telescope. So it's not just NASA. Europe is a very important partner in this.
Detto da un'americana ci fa ancora più piacere. Prego, le altre domande?
Sì,
io
buongiorno.
Non vedo. Grazie.
Abbiamo visto che le galassie più lontane sono a circa 14 miliardi di anni di luce, ma queste galassie sono identificate in una zona particolare del cielo o sono tutte attorno a noi a 14 miliardi di anni? E questo vorrebbe dire che la nostra galassia è un po' il centro dell'espansione?
No, they're everywhere. No matter which direction you look, you would see them. What's important for us is you have to look in directions of the sky that are away from our own galaxy. Otherwise, you see only what's in our galaxy because it's so much brighter. So you have to look in these regions of the sky where we're looking out of the disk of our galaxy. So these, and also which don't have a lot of bright stars in them, because again, then once you have bright objects in the field, that will swamp out the fainter things in the field. So astronomers have spent a lot of time in the past identifying good areas of the sky which give us a good view to the early universe by having not so much of our local universe interfere in the way. So naturally, because we had a lot of data from earlier missions like the Hubble Space Telescope or like the X-ray satellite XMM Newton, which was also a satellite of ESA, and Herschel, they all looked more or less at the same areas of space. And so naturally, because we already have a lot of information in those areas of space, those are the first places we look with the new facilities. So we build on the knowledge rather than immediately going off into a completely different part of sky. But there are these larger sky surveys that you can't go as deep, you can't stare at them as long because there's just not enough telescope time to do that. But you can see a broader view, and there are telescopes that do that, especially telescopes that are located, say, in the South Pole. They're very small telescopes, but you always can see, no matter, once you look outside of our galaxy, you can see galaxies at all different distances from us, also in the earliest phases of the universe. But we're not at the center. There is no, this is a hard concept, but there is no real center of the universe, as far as we know.
Ci sono altre domande? Io chiedo agli organizzatori, anche non so quanto tempo abbiamo ancora a disposizione, non vorrei neanche abusare della pazienza della dottoressa Tacconi, però l'argomento è estremamente interessante, vedo molte mani alzate.
Io avevo due brevi domande, grazie della sua presentazione prima di tutto. La prima è, secondo i suoi studi così approfonditi, secondo lei può esistere la vita in un'altra parte dell'universo, diversa dalla Terra, e se sì, con che percentuale lei stima che possa esistere? E la seconda domanda è: come avete misurato che l'universo è nato 14 miliardi di anni fa circa?
Queste sono le domande.
Okay, so the first question is, we don't know, but other missions which are studying planets within our own galaxy are trying to search for biosignatures, and that's the potential of another ESA mission in the future, to look for certain elements in the atmospheres of planets that would make one think that they're more like Earth. And we think that Earth-like planets are the most likely places to find life. Now, given that by now, whenever we look at a star, it's almost always got planets. And now I told you that there are 100 billion stars in the Milky Way. And if all of those stars, or most of those stars, or even if half of those stars have planets, then it's hard to say how many. Are we that special? It's an interesting philosophical question. Are we special, or will there be many, many other civilizations? And that's only in our galaxy. Then there are millions and millions of other galaxies, and they also have billions and billions of stars, and so those also probably have planets. Of course, no telescope that we could even conceive of could study planets in other galaxies. So that's we have to settle on our own. But that, I think the answer is, I would think the answer is yes, but we will have a very difficult time trying to actually identify what we would call life. But the likelihood of detecting signatures that would indicate life, that's very, very possible, and I expect that will happen within the next 20 years or so. And the second question, we think that, again, this is not my field of expertise, the 13.7 billion years on the Big Bang, we see it from the relics of what's called the background radiation, which is believed to be the relic of that explosion, and the properties of that background, plus the expansion and the rate of expansion, all point to the universe having formed, or the Big Bang having taken place 13.7 billion years ago.
Altra domanda? Grazie Linda per la tua risposta molto, molto chiara. Abbiamo altre domande? Quanto tempo abbiamo ancora prima di chiudere? Due domande o 2 minuti?
Faccio una domanda io.
Due domande.
Faccio una domanda io. Se è vero che l'universo si espande e non che si muovono le galassie, ma sono trascinate in modo proporzionale a distanza, si staccano uno dall'altro, si allontanano una dall'altra le galassie. C'è il problema di quelle galassie, chiamiamole periferiche del sistema dell'universo, che potrebbero viaggiare più della luce, della velocità della luce. Quando le vedremmo, se è giusta questa mia domanda? L'altra domanda, poi basta. È vero che l'universo è evolutivo, non è statico. Siamo nella fase della nascita ancora delle stelle, o che le stelle, parlo della Via Lattea, sono già nella fase di diminuzione come numero, che arriverà forse fra 300 miliardi di anni allo spegnimento totale delle stelle?
Okay, so as far as we know, nothing can travel faster than the speed of light. So yeah, all we're ever seeing when we're looking back in time is basically how long it took that light to get to us, and that's where we get these the numbers like 13 billion years. So even in our local universe. So say, for example, the center of the Virgo cluster, that light left that galaxy 50 million years ago. So it's already, this was before we were even really there. So the light that we're seeing from these early galaxies left that galaxy before the sun was even formed in many cases. So it's a hard thing to sort of get around. Sorry, what was your second question again? Could you repeat the second question?
Essendo l'universo evolutivo, siamo nella fase della continua nascita di stelle o nella fase lentamente, forse nei 300 miliardi di anni, si era spento l'universo?
Okay, so in our local environments, as I said, the amount of stars that are being created has declined with time, but we never really run out of fuel because there's always some material still coming in. But then as the galaxies themselves, as the stars evolve, they eject material that doesn't necessarily leave the galaxy, and that can come back in and then form new dark, dense clouds from which new stars can form. So although it goes down in a galaxy like our Milky Way, and eventually it could stop completely, that takes a bit of time. Now, there seems to be a critical mass when galaxies truly do shut off their star formation. And so these very massive galaxies don't seem to be forming any stars again anymore. These are the ones that look more elliptical-like, less spiral-like. These are hundreds of times or thousands of times more massive than our Milky Way. And there we think that what's happening there is that because along with the galaxy, the massive black hole in the center also grows, and these tend to eject lots of material so far that it doesn't fall back onto the galaxy. And that can act to, at least we think, it's all hypothetical because we don't have proof, but we think that might be a key point, a key piece of information that it could shut off star formation completely in some galaxies. But I don't think it will ever completely cease in the universe. But again, we won't be around. That would be billions and billions of years from now, and we won't see it.
Ancora una volta effettivamente parliamo di distanze temporali che ci sorpassano, non saprei come altro dirlo. Forse c'era un'ultima domanda, poi congediamo la dottoressa Tacconi che ci ha così gentilmente concesso il suo tempo questo pomeriggio. Prego.
Buonasera dottoressa, si è mai sentita sopraffatta dalla grandezza dell'universo?
Every day, every time I think about it, yes, every time I think about it, which is, I mean, I think one of the things that it's that feeling of overwhelming, but the feeling that there's so many interesting questions to try to answer is what drives people to study the universe. It's, I think once you get it caught by this bug to want to understand the universe, you never stop wanting to understand, and every time you think you've made a step forward, 3 or 4 new questions pop up, and then you go to answer those. And so yes, it's overwhelming, but it also keeps life extremely interesting and a lot of fun too, I have to say. I don't think I would have chosen to do anything else.
E io penso che questo sia un po' il sentimento che abbiamo avuto tutti oggi, no? Ascoltando questa conferenza. Chi non è sopraffatto dall'immensità dell'universo, chi non è affascinato, come dicevo all'inizio, da tutto ciò e da tutto quello che abbiamo visto, è il motivo per cui io ringrazio veramente tantissimo la dottoressa Linda Tacconi per essere stata con noi oggi.
Thank you so much again, and again my apologies for not being able to meet with you in person.
Quindi Linda, come puoi vedere c'è stato un pubblico veramente molto caloroso e molto numeroso, quindi noi ti aspettiamo magari un'altra volta di persona qui a Bergamo perché tu possa venire a parlarci dal vivo ancora di questo argomento veramente, veramente affascinante. Io ringrazio tutti voi per essere stati qui oggi, ma prima che ve ne andiate ho una comunicazione di servizio da farvi, perché se siete degli appassionati di spazio come me, vi interesserà sicuramente la conferenza che inizierà dopo questa alle 17:30, che riguarda la possibilità di deviare un asteroide. Avrete tutti sentito parlare recentemente della missione DART della NASA, anche questa sempre con una collaborazione dell'ESA, per imparare, studiare, testare come deviare la traiettoria di un asteroide che potrebbe eventualmente colpire il pianeta Terra. Noi dalla Terra osserviamo tutto, non osserviamo soltanto l'universo, ma osserviamo anche tutto quello che si muove intorno al nostro pianeta. In ESA abbiamo proprio un ufficio che si occupa di monitorare anche tutti i debris, i rifiuti spaziali che circondano la Terra, e fare attenzione che questi non colpiscano non solo la Terra, i debris in realtà bruciano attraverso l'atmosfera, ma che non colpiscano altri satelliti, e soprattutto monitoriamo gli asteroidi e l'avvicinarsi di potenziali asteroidi pericolosi. Quindi insieme alla NASA studiamo come deviare questi asteroidi, e ce ne parleranno quindi alle 17:30 Davide Perna dell'INAF di Roma e Edvige Pezzulli, sempre dell'Istituto Nazionale di Astrofisica, quindi vi invito calorosamente a tornare e a seguire anche questa conferenza sempre sul tema dello spazio. Grazie ancora a tutti per la vostra attenzione. Grazie ancora.